All right, so chapter 3, test review. Again, trying to prepare for Wednesday's exam. Again, we've got 15 problems that we want to work through here. Obviously, this is going to, well, at least the intention here, I should say, is that we're going to do 15 problems that are similar to the types that you're going to be seeing. But I'm sure that there's one or two that'll show up on that test that aren't here, and there's probably a couple here that maybe aren't exactly on that test. But again, you're going to use the same type of approach, same type of mentality. So jumping right in here, first problem, it says that if $3,000 is invested in a long-term trust fund with an interest rate of 6% compounded continuously, what is the amount of money in the account after 30 years? So first thing that I want to notice is that we're compounding this continuously. That tells us which formula we're going to be using. Again, thinking about our PERT formula, the amount is equal to principal times e raised to the RT power. It's just the exponential model, but we have specific values to put in place. So once we know the formula that we plan to use, the next thing that's important is going to be to know our calculations. The amount, that's what we don't know. Principal, it says the amount that we're investing initially is going to be $3,000. Let's see what else. So the rate is 6%, so we have to make sure to put that in decimal form. So to move that decimal point over 2 places to the left, we'd say 0.06. And then the time frame is also very important. We know that we're going to be going for 30 years. So the rest of this, we just have to put in place. Again, the amount is equal to, again, the principal of $3,000 times e raised to 0.06 times t. So if I were to calculate this, let's see, we always have to take care of our exponents first. 3,000 times e raised to the 1.8. So again, I know that most of us in our calculators, we can type this directly in. And we should end up with an amount of $18,148.94. How we would approach that problem. The next question is asking, how long will it take for the investment to double? So after 30 years, we went from $3,000 to $18,148.94. So we way more than doubled. So we're just saying that, hey, if we still invested that $3,000, how much time is going to have to pass in order for this to double? So we're still compounding continuously. We're still initially investing $3,000. The rate's still 6%. We're still using the PERT formula, but this time I actually know the amount. Okay, again, we know that the principal is still $3,000. As we said, we know that the rate is still 6%, so 0.06. The difference is that now I don't know time, but if I'm trying to double my investment of $3,000, twice as much would be $6,000. So now, plugging right back into that same formula, we'd say that our amount, $6,000, is equal to the principal of $3,000 times e to the r 0.06 t. So the shift of this problem is that now we're trying to actually calculate for one of the variables, not A or B or something like that. So the way that we go about solving an exponential function, hopefully you recall, is that we'd have to begin by getting the exponential portion by itself. So I need to get rid of that 3,000 by dividing it out. So the right side is going to simply become e raised to the 0.06 t. The left side, 6,000 divided by 3,000 is going to be 2. To get rid of e, I have to apply the natural log. If you do that on the right side, you've got to actually do that on the left side. So on the left side, we have the natural log of 2 is equal to, on the right side, after the natural log and e cancel, we're left with 0.06 t. So to finalize this, I'm going to divide by 0.06, which is going to create the isolation of t. So t is equal to, again, the exact answer, the natural log of 2 over 0.06. But to figure out, again, decimal version of this, we could say that that would be about 11.55 years. So again, if you, at 6% continuously compounded, if you invest $3,000, it will double at 11.55 years. All right. So the second problem we want to take a look at says that the number of units sold for a certain product is N equals 1,400 times the natural log of 7t plus 6, where t is the number of years after the product is introduced. What are the expected sales after 2 years after the product is introduced? So, again, understanding the problem here, hopefully it's pretty straightforward in this particular case. We're given the model, n is equal to 1400 times the natural log of 7t plus 6, and then it basically just comes right out and tells us that, yes, we should let t equal 2. So to rewrite my model, we'll say that n is equal to, we still have 1400 times the natural log of 7 times t plus 6. The only difference now is that instead of t, we know that t is equivalent to 2 if we're talking about 2 years. So to clean this up, we'll say that n is equal to, again, we still have our 1400 times the natural log, but inside the parentheses, we know that 7 times 2 is 14. 14 plus 6 is going to be 20. So a lot of calculator work from here. 1400 times the natural log of 20. I'm getting 4194.025. So I think that we can safely say that about 4194 would be the expected sales. All right, next up, again, we've seen multiple problems like this. This one's got a little bit of a twist to it. It says that the number of bison per acre of range in the wild is n equals 2.5 times 10 raised to the 5 minus 0.004 W, where n is the average, or I'm sorry, where n, is the number of bison per acre and W is the average weight of the bison in pounds. We want to find the average weight of a bison in a herd that has an average of 3 animals per acre of range. Okay, so trying to sort of sift through and understand this problem, like I said, that's more than likely going to be our challenge. They give the model, again, just to rewrite it down here, n is equal to 2.5, I'll use parentheses, I prefer those, times 10 raised to the 5 minus 0.004 W. So within the model, they gave a lot of useful information there, yes. To read on, it says that n represents the number of bison per acre. W represents the weight, the average weight of the bison in pounds. All right, so kind of weird that we almost always use that variable of time as an exponent here, so we're kind of breaking away from that. Our job is to find the average weight of a bison in a herd. Okay, so the average weight of the bison in a herd, that tells us that we're actually trying to find W in this case. So please keep that in mind. We're trying to find W. So find the average weight of a bison in a herd that has an average of 3 animals per acre of range. So basically what they're asking us to do is to find W when, I can't spell when apparently, that's embarrassing. When n is equal to 3. So if we know that n is equal to 3, our job is then to find W. That's what they're asking us to do in this problem. So to do exactly that, we'll let n equal 3, and now we want to go about solving. So I'm going to try to move this over. That is weird, but we're going to go with it. All that stuff over. All right. So go ahead and actually solve this. We have to stay true to the order of operations. If you're thinking, all right, I'm just going to multiply 2.5 times 10, that's not the way that we want to go about doing this. Remember, this is an exponential function, which means that we have to get the exponential portion by itself isolated as quickly as possible. Excuse me. Oh, my goodness. All right, so I'm going to divide both sides by the 2.5. That should help us on our way, so to speak. So on the left side, 3 divided by 2.5 is going to be 1.2. On the right side, that's going to leave us with 10 raised to the 5 minus 0.004 W. Where to go from here? Now, the weird thing about this problem that maybe some of us are coming to is that we've grown very accustomed to having a base E right here. And it just simply isn't base E. So remember that if we had base e to some exponent, then we would always come in and we'd say, all right, well, we'll cancel that out with the natural log. So if you're thinking that we should apply the natural log to both sides, I have to disagree. But rest assured that we actually are staring at the answer almost exclusively here. We have base 10, which means that if I bring in the log, which is going to be base 10, on the right side and the left side, now we'll still have our cancellation. Just remember, this is base 10, which on the right side is going to create that 5 minus 0.004w. The left side, we still have log base 10 of 1.2. Put that in parentheses, so there's, like I said, nothing lost. Okay, now it's all about getting w by itself. So I'm going to subtract the 5 over, which on the left side, I'm just actually going to leave that written as negative 5 plus log base 10 of 1.2 is equal to negative 0.004w. Trying to really truly isolate the w, I'm going to divide both sides by negative 0.004. We're getting close because my left side is just w, the right side is going to be this mess, and when we calculate this out, what I end up with here, 1230.2. So we would say that the average weight of the bison would be 1,230 pounds. Sorry, it's calculating as I go here. So about 1230 would be the overall weight. So again, are we going to see a problem exactly like that? I mean, I doubt it. But this is, again, it's another of our logistic growth models that we're putting into action. Okay. Again, are we going to see problems similar to it? Of course, but this one had a couple of twists to it. Like I said, the fact that we were not using base E, we were not using natural log. We had no care of time, I suppose, which that kind of breaks away from what we've been doing. All right, so back to some of the more straightforward type questions. As we can see, the directions just say to solve for x. You will most definitely have a portion of your test that looks something like this. So to solve for x, remember, we always want to use the 1-1 property if at all possible. So I think that we could rewrite 1/4 as 4 to the negative first power, which is still to the x. You're fine money. 256 is going to be 4 to the 4th power. So to clean this up, if I were to distribute 4 to the negative x is equal to 4 to the 4th. So we can do it. We've shown that we can actually use the 1-to-1 property. So my exponents, negative x and 4 are equal to each other. Now I know that x equals negative 4. Right over to the second problem. Again, every time we can use the 1-to-1 property, we will. Not exactly certain if we can pull it off yet in this problem. So if I were to subtract over, again, I'm trying to isolate the exponential here. So 5 raised to the 2x minus 3 is going to be equal to 62. And I could just get a bad feeling here that I could try to rewrite 62 to where it's an exponential with base 5. I just don't think it's going to happen. So my next move, because I'm somewhat at a dead end here, is to take this exponential function and to rewrite it as a logarithm. So we could do exactly that. I'm noticing that I have base 5, so I could rewrite, excuse me, I could rewrite as log base 5 of 62, and I could say that that's equal to 2x minus 3. So the good news here is that at any time I can figure out decimal value of what we have right here. I'm just trying to catch up in my own notes here as to whether or not I've done that. Looks like I have. It also looks like I'm running out of space very quickly. So log base 5 of 62, I have that written down as 2.5643. And if that's equal to 2x minus 3, I apologize, I'm out of room, but I'm going to add the 3 over, then divide by 2, so you understand algebra. I'm sure that you're right there with me, to get a final answer that x is equal to 2.782. All right. So next, moving on to number 6. Let's say number 6, we have log base 6 of 4x plus 5 equals 3. You get quite a few ways that we can do this problem, but I'm noticing that I'm about to time out. So I'm going to upload this portion of the podcast. We'll jump back into number 6.